Hey guys, Mr. Wood back here and continuing on in chapter 4. Most of the notes we're going to do through the rest of this chapter are going to be online. I'm going to be posting notes, and this is going to be new stuff. You really, again, like I said, I think about 2/3 of you guys are following the notes, and some of you are not, and it's not going to be good to not follow the notes. But kind of the plan will be on Thursday. I'm definitely going to be back on Thursday. At least the plan is that. And had a little glitch. Everything's fine. A little glitch, but everything is fine here. I'm from my wife's office. She works out of the home here. And so I'm going to be doing a couple lectures here, getting close to, if not done with chapter 4. So we still have a little bit to go. Thursday, I'm going to be there, and I'm going to videotape for the B cohort, or for the A cohort. I'll do it in front of the B cohort, the Redox Titration Lab, the second part, or the first part. And the second part you guys are going to do on Monday, Tuesday. And I'm hoping next Wednesday, Thursday is going to be kind of a work day, a preparation day, because the week before fall break is going to be our first test, and we'll do a 2-day test as I've talked about. What is due? The gravimetric lab is due a week from Wednesday, Thursday, and I'll just the dates, and I'll give you all this, and it's all on the calendar. Getting out my phone here to look at this. The dates that the gravimetric lab is due will be Wednesday, September 30th, and then Thursday, October 1 for B cohort. And then the quiz chapter 4 and the first day of the test for chapter 1 through 4 will be Monday, October 5th and Tuesday, October 6th for AB. And then the Redox Titration Lab will be due on Wednesday, Thursday, the 7th, 8th, and we'll finish up the test. And we're going to get well into chapter 5. And again, like I said, a lot of the instruction I'm going to do is going to be online via the computer. And I'm hoping you guys, I know a lot of you are following along. You need jokes. So one thing I do every year is I always do a t-shirt for AP Chem, and I have my students design them. So I'm going to show you once in a while a couple of the t-shirts, and these have jokes right on them. So this is the joke for the day. So here is my 2013-14 HRH AP Chemistry, a polar molecule with a polar bear. There you go. Little chemistry humor. And on the back, I think it says, "I'm a chemist. You can flask me anything." So you guys can start to think about that, and I'll show you some more of my jokes. So, okay, so here we go, back to where we left off. And what we were talking about were titrations. Okay, so this slide we've already talked about, so I'm not going to go over this. And again, what the lab we're going to do, that we're going to start, which actually Miss Daly or Mr. Frederick gave you guys, was on a called a redox titration, and a lab that we just did virtually last spring was an acid-base titration. Now, some of you I know had chemistry 2 years ago, and you guys did titrations. And depending on how far we get, we will do a few titrations, one of the most common labs done in science. But you can see this big, long instrument, kind of long, skinny instrument. It's called a burette. And I'm going to talk about that on Thursday. And for the A cohort, I'm going to videotape what I do in B. And I will, I'll show you, and we'll get the data. For part 1, we'll have the same data. And then for part 2, you guys will do that. But that is a titration. Okay, so now going on, here is a kind of a classic AP chemistry. And really, I think this I don't think we would ever do a problem like this in first year chemistry. 1.50 grams of KHP, potassium hydrogen phthalate, which you really, well, you got the formula there. You really don't need it. A key thing is it says it's a weak monoprotic acid. Being monoprotic means it's going to give up one H. Is made into 1 liter solution. 25 milliliters of this solution is titrated to the end point with 18.6 mils of NaOH. Determine the molarity of the NaOH. And this here, and actually I'm gonna go back here now to my to the board behind me here. Okay. Okay, and I'm going to do this now. Now, to me, the way, again, what I always do, the easiest way to me, and a common first step, and you're hearing me say this already, and you're going to hear me say this throughout the class, is to write out the equation. And you go, I have no idea how to write out this equation, and that would be a fairly good point. And a common way to write out an acid, if it's monoprotic, hopefully you guys can see that. I don't think you can. Is HA. Let me do this in blue. HA. I'm going to move my computer a little bit closer. See if you guys can see that. So, but anyways, this is the acid. And weak monoprotic would mean it's going to give up just one H. So when I combine it with NaOH, again, here writing an equation, acid base, always going to give up water. And I could write it out like this, NaA, or I could just say a salt. But there's the equation. And you go, well, what happened to the KHP? Well, I could write that out. I could have done that. I would simplify it. And I could have just written it KHP plus NaOH makes water. And I would just say a salt, just to simplify it. But I would write out the reaction. And then if I write in what I have is I have 1.50 grams of this. And I have 1 liter of the solution, is what it says. So I make 1 liter of this solution. And I'm going to show you 2 ways to do this problem. And then you guys can choose whichever way you want. And then it says we want to find the molarity of this. And we have 18.6 mils of this. Okay, so this to me is kind of the best way I think to do this is to do stoichiometry. And I'm going to show you again 2 ways to do it, and then you guys can choose. And I guarantee you'll see problems like this not just on this test but throughout our class. And they told us the molar mass of the KHP. They said it's 204 grams. So it's 204 grams of this. So what I'm going to do is I'm going to take the 1.50 grams of the KHP, and I'm going to convert this to moles. What I did going back to this 1 liter of solution, but then I take 25 mils of this. So what I'm going to do is I'm going to convert this. So I'm going to take the 204 grams, I'm going to convert it to moles. So I've got 1.50 divided by 204 gives me 0.00735 moles in 1 liter. I have 1 liter. But I only took 25 milliliters of this. So I'm going to multiply this by 0.025. 25 milliliters, I got my, should be 0.025. 25 milliliters, 0.025 liters. And so this here came from the 25 milliliters there. Okay, so I'll take 0.00735 times 0.025 divided by 1 gives me, do my math here, 1.5 divided by 204 times 0.025 gives me 1.84 times 10 to the negative 4th moles. Okay, so this is moles of the HA of the acid. Now I'm going to go back and I'm going to do stoichiometry because I know that molarity, which is what I'm trying to find, is moles per liter. Well, I know the liters. The key here is to find the moles. So moles per liter, and so I know it's 18.6 milliliters, which is 0.0186 liters. So I took the 18.6 mils and I got it in a liter. So now I'm going to take this 1.84 times 10 to the negative fourth moles of the acid. I'll just say HA. It could be KHP. It means the same thing. And the ratio here from my balanced equation is 1 to 1. So what I'm doing here is I figured out how much moles I had. Let me see if the light on this makes it better. Maybe down here it does. Moles of acid, so I had the equation, but I ultimately want to find the moles of the base. And so it's 1 mole of HA for 1 mole of NaOH, because it's 1 to 1. And so that tells me 1.84 times 10 to the negative fourth moles of the NaOH. Okay, and then I'm going to take that and I'm going to put it right here. And if I divide that out, what I get is 0.0988. 0.00988. And that would be the molarity. So all that, now that you're looking at that and you go, that is a hard problem. And you would be right. That is a pretty hard problem. Now that is one way to do it. And to me, that is always the safe way to do this, is to do the stoichiometry part. But the other way you could have done this, and you're going to say, oh man, why don't we do it this way the first time? Okay, watch. We'll make it a mess here. The other way is the equation I have written down there. You're all saying that's Mr. Lee's making a mess, and you'd be right. Clean this up. But the other way to do this is to use that equation. And the equation I have there in the notes, but I actually add a little bit to it. What I do is I go like a dilution. So just like it says in the notes, you could do MA, VA, molarity of the acid, volume of the acid, but I add to it the number of H's. So molarity of the acid, volume of the acid, the number of H's, molarity of base times the volume of the base times the number of OH's. So in this case, if you look back to what we had, and I've erased it now, but we had this, and I still had to go through this, and I had to convert that from grams to moles, which I did before, so I'm using that. The volume of the acid, and technically, if this is kind of like gas laws, which is what we're going to get into a little bit before we leave for fall break in chapter 5, but just like on the combined gas law, as long as you use milliliters for both of these, you're okay. And so the volume of the acid that we had was 25 mils. And the number of H's were 1 because it's monoprotic, so it's 1. The molarity of the base is what we're trying to find. The volume of the base was 18.6 mils. And the number of OH's was 1. And so if I do the math here and solve for X, I think I'm going to get the same thing. And of course, you guys are looking at this, you're going, this way is way easier way to do it. Yeah, it's virtually the same thing. And so if you guys do it that way, I think that works. And I would really try some problems in the book and make sure you're good with that. So I showed you kind of what I think you guys would say and argue successfully the more complicated way, doing stoichiometry first, but that's kind of the fail-safe way. But if you factor in the H's and the OH's, you would be okay. So, and again, this is why I want to give some time for questions, because those that are following along, you very well could have some questions. Okay, so back to the notes. And doing problems like this are definitely good ones to try in class. Now, here again, so if you look on this slide, so the MAVA MBVB doesn't work for the following reactions. So actually, what you should look for, what you always should look for, is the subscript. Look for the subscript. Do not look for. So what I'm saying is when you're doing these, do not look at the number in front, but look at how many H's and how many OH's they're going to give up. And that's when you're doing the H's and the OH's, it's going to depend on the subscript, not on the coefficient. And that would be a really good thing to practice from the book, because I guarantee you, again, and I say this, this test, you can tell, is going to cover a lot of ground that you guys have coming up. But again, I would look, so in this case, I again do an MAVA number of H's. Well, there's 3 H's. I'm looking at the subscript on H. And then MVVB OH's, well, the number of OH's is 2. And so that's the way I would ignore the coefficients. I would just look at the subscripts in doing that. And this is something that's not just going to come up here, it's going to come up throughout our class. Okay, now here is another problem. It's a pretty good problem. This is another kind of an example of a titration problem. And again, I always write these things out. So a 0.3518 gram sample of waste containing CCl4 and benzoic acid. So that's the 0.3518 is a mixture of 2 things. It's the CCl4 and benzoic acid. It was titrated to the endpoint. Remember, the endpoint is where the moles of acid equal the moles of base, with 10.59 mils of a 0.1546 NaOH. Calculate the percent by mass of benzoic acid. Okay, so to do that, so back to my little chalkboard here. So again, I'm going to start out. So if I was in front of you right now, I go, okay, so what do we do first? Make my mess here. The first thing we do is we're going to need to write out the equation. So I'm going to do that. I'm going to have acetic acid. I need to get those expo markers, and I didn't have those here at home. All I had was the vis-a-vis. So hang in there with me. We'll do this problem. Okay, good enough, I think. Okay, so I'm going to write out the reaction. And here we have benzoic acid. Okay, that light kind of shines right on this. Turn the light off. So write out the benzoic acid. And here we have the formula for the benzoic acid, HC7H5O2. And again, just for review's sake, from first year chem, when it's written, the reason I'm going to do this in blue. I think blue you can see better. Yeah, and I think maybe with the light on, you guys can see a little bit better. And I'm going to leave the light off. This 5 is part of that benzoate ion, but so this is monoprotic plus NaOH. So again, I'm going to do the same thing that I did in the last problem. The first thing I'm going to do is I'm going to write out the equation that happens here. So here we go to outers and inners, and then I'm going to get the C7H5O2, the anion here with this. And again, this is why I do this every time. If you were to come in and have a problem, this is what I would do. So we have 10.59 mils of the NaOH, and we have 0.1546 molarity of this. And we really want to find the grams of this, because the question is, we want to figure out the percent of the benzoic acid in that mixture. So I'm going to find out moles. So I'm going to use moles is equal to molarity times liters. And I'm going to be finding the moles of the NaOH. So I have 0.1546 molarity times 0.01059 liters. So I got the milliliters into liters. Okay, now let's see. Okay. Okay, hopefully you guys can see that. Okay, so I got 0.1546 times 0.01059 gives me 0.0016, really have 4 sig figs, 1637 moles. And this is of the NaOH, which means now I can do stoichiometry because it's a 1-to-1 ratio. Again, I'm trying to figure out the mass of the benzoic acid. So I'm going to take 0.001637 moles of NaOH. So here I'm doing stoichiometry. I told you this to me is really the safe way to do this. So now I'm using the 1-to-1 ratio. I'll just say Ba, benzoic acid. That's what this is, Ba, benzoic acid. Keep turning the light on and off. That light is kind of on that equation. I need to move the board. Maybe that is better. So that's the benzoic acid. And then if I look up the molar mass, so for every 1 mole, I think the molar mass I have of this is 122 grams. Okay, and that gives me 0.1997 grams of Ba, benzoic acid. But okay, so that answered this part of it. But the question was, what is the percent of the benzoic acid in the mixture? Well, it told me that it was 0.3518. So now I'm going to take the 0.1997 grams of benzoic acid, and the mass of the mixture, which was given in the problem, is 0.3518. So this is the grams of the mixture, which is given in the problem. And then I'm going to multiply by 100. Okay, what I get, I keep my sig figs consistent throughout, 56.77% benzoic acid. So again, a pretty good problem to do. So, but what I did there again is I had to write out the equation, and once I had the equation, then I did stoichiometry from the data given to me. I found the moles of the NaOH, but I was trying to figure out the percent of the benzoic acid in the mixture. So I used the information to find moles of NaOH. I did stoichiometry. I found the mass of the benzoic acid, and then I found the mass of the percent of the mixture. Okay, let me just go a little bit further here. Okay, not too much more in this lesson. Okay, so we've done a couple pretty good titration problems. Again, definitely AP chemistry problems, and there's going to be problems like that. And you can see here the problems. These would be good problems that you guys can be working on in class. Okay, so the next thing I want to do, and I don't want to go go through this a little bit, but oxidation reduction. So now we're kind of going into the last part, and this is going to take a little bit of time. The last part of these chapters, but of the chapter 4. And what we're going to go over here is review. So these reactions, it's typically like the lab we're going to do on Thursday that Mr. Frederick or Ms. Daly gave you was called a redox titration. These reactions involve the transfer of electrons from one substance to another. It's always abbreviated redox. And the first thing, and this is review, rules for determining the oxidation numbers, real or apparent charge of an element. The oxidation number of an atom or in a pure element is 0. And then rule 2, the oxidation number of a monatomic ion is its charge. So when I teach this in first year chem, I actually put rules 1 and 2 together. And I said, if you ever have an element by itself, this is the way I say it, its oxidation number equals its charge. So if you have something by itself, its oxidation number equals its charge. And that's what those two say. Okay, and then this rule here really kind of comes down to an end. In a compound, you use for its oxidation number. Oxidation number and oxidation state mean the same thing. But halogens are -1, which is its ionic charge. Alkali metals are +1. Alkaline earth metals are +2. So in this case, you use the oxidation number is its ionic charge. And then this is what I always have as rule 2. So rule 1 to me is something by itself is always the charge. Rule 2 is oxygen in a compound, its oxidation number is -2, which is easy to remember because its oxygen's ionic charge is -2, except as a peroxide. And so if you have H2O2 or Na2O2, where you have O2 something in a formula, that's a hint that there's a peroxide. And in AP Chem, there's a chance you could see that. And they're in OF2, which I don't think even me and my cruelness asked that. Hydrogen in a compound is +1. Okay, and then the sum of the oxidation numbers equals the sum of the molecular ion. Okay, so let's just do a couple of these, and then I'm going to leave it there and have you guys look at a couple that we'll look at in class. Okay, so let me just real quickly, because you guys, if you've been following along here, you've been listening a good long time. Okay, so I'm going to go back to my board here. Don't make it all messy again. I got to bring home some Expo markers in case we did all remote. Okay, so what I'm going to do here, what I'm going to do on this problem, so this is kind of different than what we did earlier in this lesson, is I'm going to be assigning oxidation numbers or oxidation states. So my half blue board here. Okay, so I'm going to do 3 of them. This is what I would do if you guys were in front of me in class. Okay, so the first one, these are the ones I would have us do. NO3, -1. We're going to assign the oxidation number for an N and O. CO2 and K2CRO or CR2O7. K2CR2O7. And so we're going to assign the oxidation number for all the elements in these. So in the ions, so I know a couple things. I know oxygen is a -2. And I know that the oxidation numbers need to equal the charge here. So the charge is -1. So oxygen is -2 times 3 is -6. And it needs to total -1. So again, a couple rules here. Is whatever the charge is, the oxidation numbers need to total the charge. If the charge is 0, then they need to total 0. Oxygen, each oxygen's -2, and there's 3 of them, so it's -6. So I call it fill in the blank. So what would N have to be? So a positive 5 and a negative 6 is negative 1. So N would be a positive 5. Okay, and CO2. Well, this one, it has no charge, so the oxidation number would equal the charge, so it's 0. Oxygen is negative 2. Negative 2 times 2 is negative 4, so again, fill in the blank. And again, the only time oxygen is not negative 2 is when it's a peroxide, or OF2, which I think hardly ever comes up, or is by itself. If it's by itself, then it would be 0, so it's fill in the blank, so carbon would have to be positive. Okay, so here would have been the answer for the nitrate ion. Here would have been the oxidation numbers for CO2. Okay, the last one, so this has no charge, so it's 0, it needs to total 0. Again, I know that oxygen is negative 2, so negative 2 times 7 is negative 14. I gotta know one of these. And so here's an alkaline metal, so I'm gonna use the ionic charge on potassium. So potassium is positive 1. So positive 1 times 2 is positive 2. So fill in the blank. Now, if you look at this, you go, it should be positive 12, but there's 2 of them. So I'm going to take positive 12 divided by 2. So CR here would have been a positive 6. So that would have been a positive 6 times 2 would have been a positive 12. So here would have been the oxidation numbers of the K, the CR, the O of potassium dichromate. Okay, and this is what I'm going to leave you with. Here are some to try, and I'm going to try these in class next week. SO4 negative 2, see if you can find the oxidation numbers for the S and the O. Na2CO3. Okay, again, see if you can find the oxidation numbers for the Na, the C, and the O. And then finally, HPO4, the charge right here, I think it's negative 2. So this is the hydrogen phosphate or the biphosphate ion. So see if you can figure out the oxidation numbers for sulfur and oxygen and sulfate, for sodium, carbon and oxygen and sodium carbonate, and hydrogen, phosphorus, and oxygen in biphosphate. Okay, guys, I'm going to be posting some more lessons, so keep following along. Talk to you soon. Bye.